Today we're talking about the Modbus communications protocol. Modbus, the protocol, was originally a proprietary protocol that was owned by Modicon, and so it was only a protocol available on Modicon devices, or I guess you could say Modicon approved devices, as a means of communicating over an industrial network and networking devices together. Nowadays, Modbus is open source, so it means as a user of Modbus, you could tweak the protocol, come up with your own function codes, your own data types, your own addresses, and so on, and use Modbus for your own specific functionality. Back in the day, when it was owned by Modicon, all of the addresses for the different data types, whether it be DIs, DOs, analog inputs, analog outputs, they all had specific register or memory locations as addresses that were the same from one device to another, all dictated by Modicon. But now that can all be changed or tweaked or specifically configured for your own purposes. So even though Modbus wouldn't be considered a true SCADA protocol because of how wasteful it is with bandwidth, and for reasons that we'll see going forward when we start studying something like DMP3, it has a number of if you want to call them inefficiencies in its protocol, and we'll look at what those are and how they are addressed with a true SCADA protocol. But you'll still see Modbus used lots in wide area network SCADA systems, and as we go forward in this course, we'll explain more of why I think that is and so on. So in any case, what we're going to do is we're going to be looking at this protocol in more detail now for the next several weeks, and really learn what it's about and how to interpret messages and to explore its functionality. So first of all, what I want to do is just look at comparing a business network to an industrial network again, and starting with the business network on the left here. Business networks are peer-to-peer, and so if we look at the cloud representing the network here, this is a multi-drop network that could be implemented as RS-485, it could be Ethernet or any other, or a WLAN network, any other multi-drop network of which all devices can talk to any other device. And in a peer-to-peer network, each and every workstation within that network has equal rights to the network. So it means that there's no hierarchy, I guess you could say, to these devices, and this means that when it comes to accessing the network, with everyone having equal rights, there is an actual potential where all four could be trying to access at the same time. When that happens, the network itself and the protocol has caused a collision domain. And that collision domain results in all sorts of issues when it comes to communications over the network. It can cause things like latency. So it means that you don't have a real-time component. It means that data could arrive at the destination far later than what would be considered real-time. It could take some time for that collision to be resolved, communications to follow an orderly format, and for the data to arrive at its destination. It can result in, even in severe cases, loss of data. And it means that the data doesn't arrive, and there needs to be a retransmit or a session built again to to move the data from one workstation to another. And really, when it comes down to just those two issues, this is something that would never be acceptable on an industrial network or a SCADA network. When you think of an industrial network, it's monitoring a system of which is of, or a process which could even have, it has consequences that are severe in a process, to have latency or to lose data. In a business network, you would tend to say that's not really the issue, or it's not really an issue that becomes affects essentially any kind of quality of life or loss of life, like some of these high-level processes that could be catastrophic in an industrial network aren't considered catastrophic in a business network when it comes to maybe not receiving an email or being able to get a file right away or having to request that file from a server again. So this is really what we're looking at addressing with industrial network protocols like Modbus. When we look at Modbus, Modbus is a master-slave, or maybe the more politically correct term these days is client-server, where we have a client or master continually polling each one of the slaves or servers within the network in something called a polling sequence. So we have requests and responses that go on in the as part of the polling sequence one at a time. So if we think of these as being our servers or our remotes, these are all names that are used for these remote devices out in the field, whether they be substations or gas compressor stations or whatever. We have servers, remotes, or slaves. So the master, the client, the Modbus master or client, polls each one of these servers one at a time. So it would start with server 1, send out a request. It would be waiting for a response. Once a response was received, it would move on to server 2. Do the same. Move on to server 3, move on to server 4, and then it would just keep on cycling through this polling sequence and retrieving data and requesting control if it wanted to, say, close a valve, trip a breaker, open a gate, things of that nature. So this is the master-slave polling sequence, or the client-server polling sequence, where we have a very organized protocol for communications where there is no longer a collision domain. When we bring in a polling sequence with master-slave polling, we've avoided a collision domain in the network. And of course, then we've got what we can rely on as real-time data, a real-time snapshot of what's going on at any one of these server or remote locations. And we shouldn't have any loss of data unless there's an absolute communications fail, because we've avoided the issues of a peer-to-peer protocol or a peer-to-peer architecture. So that's the first thing I wanted to address when it comes to Modbus and an industrial communications protocol is a master-slave or a client-server. So when it comes to SCADA functionality then, and we have this polling sequence going on, right? Polling all of these devices in a ring, if you will. The functionality of the master to the slave is that we want the master to be able to remotely monitor and control and retrieve data from the server location. And when we do, we are essentially looking at moving the data that's found in its data map It's called the data map or the database at the server. We're looking at essentially moving the server's data map points, the values of DIs, DOs, AIs, AOs, and counters and accumulators. We're looking at moving that data from the server location through the network back to the master. And so when we look at SCADA functionality, we have to look at the functions that would be built into the communications protocol in order to work with these data types within the server data map. And really, the way I would put it next is when we look at the functionality that would have to be in the protocol, let's think about a digital input or an example of a breaker status. Is the breaker tripped or closed? Is the switch open or closed? Is the gate open or closed? Doors or valves or whatever. What is their status? Is it open or closed? On or off? 0 or 1? Those DIs need to be monitored by the master. The master wants to know the status of those devices. And so when you look at a DI and the functionality that the SCADA protocol would have to have in order to determine that status, you'd be looking at a read function. So when we look at an input data type like a DI, the functionality we would need we'd need to be able to read it, right? So remotely we want to read a DI. Well, it would be the same thing for the analog input data type. Notice it's an input data type, so we would want to be able to read it as well. When it comes to a DO, which is an output, this is where we're controlling a breaker, controlling a valve, or controlling a switch. The master wants to be able to turn on or off that switch or trip or close that breaker. And for that, we would need to have the functionality to write. So the master would actually send out a write command to the server to load a 1 or a 0 into its output register so that it could control that breaker. So notice that's an output data type. So an output data type, we'd be looking at having the write functionality. So then you would follow for an AO, you'd be looking at having the write functionality as well. Okay. Now, here's what's specific about an output data type. Not only do we want to be able to request to close a breaker by writing a value, we also want to be able to check to see what is the value that we wrote. What is the value in that register? Because if the breaker didn't trip, where's the problem? Is the problem in the actual writing of the register or in the field equipment? And so we always want to have the functionality to actually read an output data type as well for confirmations, right? So we would have a read functionality here as well, and a read functionality here. So what it means is that when we write it, we also will be able to read it. And so for output data types, we're looking at read-write functionality. For input data types, we're looking at read functionality. So if we were to look at our Modbus protocol as we go through, we should find function codes to read DIs and AIs. We should find function codes to read DOs and AOs. But further, we should find function codes to write a DO and to write an AO. Now the last one is counters and accumulators, and that's kind of a special one which we'll talk about later. They can either be configured as read-write or as read-only. So when we go through Modbus, we should be able to identify this functionality in the protocol itself to be able to do exactly that. What's really the overall aim or goal is for the master to have a true snapshot or real-time picture of what's going on at any one of these servers by the use of a master-slave protocol, requesting and waiting for responses responses that are things like monitoring the status of of digitals and reading analogs, controlling breakers as in DOs, or controlling a variable output as in an AO, and then retrieving data files that could be a table of trends of a particular input and things like that. So hopefully that kind of just gives you a little bit more of an idea of what we need from a industrial networking protocol when it comes to avoiding collisions, and what we're looking at retrieving for server data from a server or a slave. So if we're looking here, this is really an example of what we just talked about. Here's our control center. This is our master control center. This is where your system operators, your chief engineers are sitting, and in a SCADA network in particular, we don't really have we don't have automation as part of the SCADA network. Any automation goes on locally within specific PLCs, DCS, or other automation type networks. When it comes to SCADA, it's really just about retrieving data, statuses, and analog values from remote locations and bringing them back to a master control center where system operators and chief engineers can do the controlling of the process or the system. So that's what we have going on here. Notice how then when it comes to the wide area network connection, we're using a SCADA protocol called DMP3, and we're going to look at it later. And this is really a true SCADA protocol designed for wide area networks. So we've got a DMP connection out to all of these remote sites, or these server sites or slave sites. It says we were operating it within the TCP/IP packet protocol, and it's saying it's 10 kilometers. So we're definitely employing datacom, which would look like an Ethernet connection to this remote, and this remote has taken on a unique identity as within the network of RTU number 33. So if we look locally at that site, what we have is Modbus as the master-slave connection to for the RTU to be a master to the local area network, sending out a request to this IED. Remember, that stands for Intelligent Electronic Device. And notice how it's got a unique identifier as well on that local area network, IED number 4, sending out a request and obviously waiting for that response, and then moving around to all the other IEDs in its Modbus network. So this is where RTU 33 is our Modbus master locally at the substation. This is all within the substation compound, right? So this is local. So at this LAN, we have in this case, a GE RTU, a D25, sending out a request to IED number 4, getting a response, a Modbus response, of course, and it's using a Modbus request to look for AI at address 0. So this is actually, may not look that way, but it's AI number 0. And this would be the field wiring connection for an analog input to this smart meter. So locally at the substation, we've got the RTU here as a master requesting through a polling sequence all of its IEDs for data. In this case, IED 4, it's looking for analog input 0 to be reported back from what this smart meter is reading over that 4 to 20 or whatever it might be, to collect maybe a 1 to 5 volt or a 4 to 20 milliamp loop to get that analog information. It says it's being communicated over RS-232. So therefore we could say that that's a point-to-point connection. Notice how it's under 50 feet, 10 foot length. Know that that would be a null modem connection, wouldn't it? Because it's terminal to terminal. Null modem. or crossover. So once the RTU has the information from all its local area network connections, then the RTU, remember, is a data concentrator. And so what's the job of the data concentrator? To gather all the data via communications to, at its local area network connections and concentrate it into one database. So now I've got that data map here with DIs, DOs, AIs, which is coming from here, and AOs, leaving counters, accumulators out for now. It's concentrating all in one database that now becomes the server database to the wide area network. For the local area, the RTU33 is the master. It's the client for the local area. But to the wide area, the RTU plays the role of server or slave now. So this is the slave or server to the wide area network. Okay, and that's really what's being demonstrated here. Here is the data map of IED number 4. And we can see how the databases are being communicated through the system to reach the master control center of where RTU33 has its spot within the master database or master data map. Master database. And the information from one particular IED in the substation is making its way through the SCADA system using data communication protocols. What's the data we're moving? Analog input at location 0, in this case I guess 12 kilowatts, is being transferred using Modbus through to the RTU33 on site at the substation. This is now the RTU's server database, which is served up to the wide area network using DMP3. So that's really the idea in this system, is to take I/O data from smart devices within the substation and move them through the network over local area connections to wide area ultimately, and bring it back to the MCC or the Master Control Center. How's all this functionality happening? Through data communications protocols of DMP3 and Modbus. And what are we looking at today? We're looking at exploring Modbus in more detail. So that's just through these illustrations. You can see these lines coming in, how it shows the process of moving the data through, this last one being DNP3, to populate the master database. Now, this master database would be referred to as the real-time database at the MCC. And this would be the database that's accessed by SCADA engineers. It would be accessed by HMIs in order to build objects and maps and a layout of the different substation single line diagrams, an overall map of the city or the province, including data as part of objects on the HMI. So this would be called the real-time database. But realize that when the SCADA master at the control center comes around to polling RTU33 again, the data that was real-time now becomes what's called historical data, and that data is just put over or pumped over or ported over to the historical database now, so that you can look back in time to see what previous real-time values were. But as soon as we have another poll coming around to RTU 33, what was in there becomes historical, and the new data going in is what's called the real-time data. It's a real-time snapshot of what's going on at that remote location. So this is what's just being shown here, is the local area. It's calling the scan sequence. You'll see it called that. I most often call it the polling sequence. So in this polling sequence, we have the individual clients or masters at each location working on their polling sequences. And then, of course, you've got the MCC polling them as well, right? So you've got these higher levels as you move up. Now this MCC could be a server or a slave to a higher connection. Let's say this is, say, NMAX. NMAX could be reporting to ASO, right? So you get the idea. There's this whole hierarchy to it, where you have local area master slave connections reporting to wide area master slave connections that can further report to wider area connections, as in ASO covering the whole province. So I think you get the idea. So that's what we see illustrated here, is local area connections spread out over wide area and being collected by the MCC. And you can see that's what's being shown there. Okay, when it comes to the Modbus basics, Modbus is popular for being a simple and easy to understand, to train, to configure protocol. So it's very effective in that way. It lacks a lot of things as far as a SCADA protocol goes, but with the kind of bandwidth we have to work with these days, at a very cost-effective, being very cost-effective for high bandwidth connections, we still see Modbus used a lot. I often say that because of our cheap or inexpensive high-speed connections these days, we can afford to be wasteful with our bandwidth, and therefore Modbus still has a real kind of foothold in a lot of these networks because of that. You don't need to bring in the complexity of something like DNP3 when you can be wasteful with your bandwidth. That's the best way I can put it. Okay, so Modbus, of the OSI model that we talked about, it uses layer 7 and layer 1. So not all protocols have to address every layer of the OSI model. However, in order to move that data over the internet, you would have to use all 7 layers. But when it comes to the protocol itself and moving it through a local area connection, in this case, it's only addressing two layers of the top one and the bottom one. And it's widely implemented through many utilities: gas, water treatment, power, you get it. And it's used local area for automation too. Used for equipment and software, HMIs, RTUs, IEDs, PLCs. Modbus is a master slave or client server communications protocol. Slaves are referred to as remotes or servers as well. So we're going to start to look at the Modbus protocol now. We're going to list the 4 major components of a Modbus message. And if we look at our Modbus handout, we'll be able to identify these 4 major components by looking at the very top of the first page of our Modbus handout. And our Modbus handout is our primary resource whenever we're going through any Modbus exercises, Modbus videos, Modbus presentations, Modbus quizzes and exams or labs. Is our primary and major resource in our toolbox is our Modbus handout. So you should have it with you as you're going through this presentation or anything else to really learn properly how to interpret and understand Modbus. So we're going to list the four components. We're going to interpret and create a Modbus request and several response messages. A Modbus request is always a message from the master to the slave. A request is always the result of a client sending a message to a server. That's always a request. And what do we want to do? Just like we said, we want to read or write. So if we're going to read, we're going to read things like an DI, an AI, or a counter. We're going to read a value of a breaker status. We're going to read a value of a current or voltage as an analog, or we're going to read the number of times a breaker tripped, a valve closed, a gate opened, a door opened, whatever. Or we want to read an AO or DO as a confirmation. And remember, we talked about that. There's times where we want to read an output data type. We want to write an output data type in order to, as an AO, to set a set point. So a set point for, say, a motor RPM or a pressure or a tap changer on a transformer. Or we want to, as a DO, trip a breaker. How is all that done? With a write command, right? Master is requesting control or data from a server or slave device. This is what happens with a request. A response then is always from server to client, or from slave to master. And this is where the remote, the server or the slave, is responding with data from the field devices in its local area network. So again, it could be DIs, AIs, counter values, or DO or AO confirmations, right? Confirming what was written into those data types or those memory locations. So a Modbus frame has four main fields for all requests and all responses. So these four main fields are consistent between a request or response. They don't change. We can identify each of the fields in either a request or a response. The first one is the address. And the next one is the function or function code. The next one is the data field. And then the last one is the error check field. So those are the four fields that we can identify in every Modbus message or every Modbus frame. Notice how we're using the word frame. That's used for asynchronous data, a frame, a data frame. So this is a Modbus frame or message that is for a request or a response. So now what do these fields represent? First of all, we have the address field. And look at specifically, we are talking about a request here. So when we look at this and identify the configuration of each one of these fields, we do need to be specific as to whether we're talking about a request or a response, and we'll see the reasons for that as we go forward. But for now, just understand we're looking at a request here for this first one, and the address contains the unique server identifier. So this is our unique server number, right? Because if we're going to have a multi-drop network and we're sending a request out over this multi-drop network, we've got to be specific as to who we're requesting from or who we're talking to. So we're going to call that server by name or call that server by number. So this, oops, I kind of overwrote that, but it's always 1 byte in length. So when we look up here at the address field, what's its size? It's 8 bits or 1 byte. It's always 8 bits or 1 byte. You can't change that. So valid addresses are 1 through 247. Now, if you know anything about binary to decimal conversion, 8 bits gives you a range of 0 to 255 base 10. So you may be asking, why do we not have a total of 256 addresses, or all the range there? Well, the reason is because there's reserved addresses. So when it comes to address 0, this is what's called a broadcast address. So if you were to put an address 0 in the address field, which would be made up of 8 bits, so therefore it would look like 00000000 as 8 bits in that address field to give you a total of 1 byte. You would be sending what's called a broadcast message. That broadcast request would be one where you're directing a write command to every server on the network. And now realize that I was very specific about that, and I said that would be used for a write command. It wouldn't be used for a read command, because then you'd be asking everybody to give you a response to that read, and as a result, you'd have a collision on the network. You'd be asking for a response from everybody as opposed to somebody specifically. So with a write command, you can send out an instruction to do something without expecting a response, but to send it out to everybody simultaneously. An example of that is system reboots, where you're telling everybody to reboot at the same time, but not wanting a response. You're telling everybody to synchronize their clocks to a certain time. You're doing a write command that is where you're not looking for a response to come back, but you're sending out an instruction. So that's an example of what's called a broadcast message. Address field contains 0 or all zeros for that. Okay. Now just going back here to answer the question, what happens to addresses 248 to 255? Those are slave addresses that are reserved for special purpose. So that means, being that Modbus is open source, you could use those specific addresses for your own special purposes and build a specific purpose into your protocol to customize it. Okay, so when it comes to the response for the address field, so now you've got to be aware we're looking at the response. It's still always 1 byte. That'll never change, so that's 8 bits. But further to that, when it comes to a normal response, all the remote does is echo back its own address in that field. So that means if you see a request going out to slave 23, that in the response, the slave will put its own address in the address field in the response. Essentially, it would be saying, yes, this is 23, here's what you asked for, or here's a write confirmation, or whatever. So it echoes back its own address, and that's a normal response. Valid addresses, once again, then are going to be 1 through 247. And then the question comes up, could there be a 0 in here? Because this is a response, you'd never have a 0. Zeros or broadcast messages are only found as requests. So the 0 broadcast will only be a request. And I think that makes sense, right? If you're sending out an instruction to everyone, it's an instruction that comes from the master or the client, so it would only be found in a request Modbus message. You'd never find a 0 in the address field for a response. So now we have the function field. This is called the function code. And this is where you're going to find your reads or your writes. oops, your reads or your writes, and it again is always 1 byte. It doesn't change, and that's 8 bits. And further to that, we'll say 2 hex numbers, because it takes 4 hex numbers. It takes 4 bits to represent a hex number. So if you have 8 bits, that's going to require 2 hex numbers to represent that 1 byte of data. So these master function codes are known as operation codes. Do you want to read or do you want to write? And these read or write commands are specific to a data type. So we would expect to find function codes to read DIs, read AIs, read a DO, or read an AO. And lastly, we would want to be able to read an ACC or an accumulator as well. To write, we'd want to find the write functionality for DOs and AOs, and very specific, we'll talk about that. There's times where we want to write a counter or an accumulator as well. So it means that these operation codes, or these function codes that are assigned to a specific data type, will find all that functionality in our Modbus protocol. Is that when we look at these function codes in as the second byte of a request or a response, they will be indicating a read or write on a specific data type. And if you were to look at your Modbus handout right now, you can see a list or a table of the most popular function codes. They aren't all the function codes, but it's the most used or popular of all of them. So this is the Modbus handout. This is the resource I talked about, or the document that you want to have with you whenever you're doing any Modbus exercises, labs, exams, or even going through this presentation. It's your primary resource to do all Modbus message interpretation, creation of a Modbus message, in order to understand the protocol. This is really the number one tool in your toolbox. So I just wanted to go over it now that we've gone through part of the presentation already. And if you recall, at the beginning of the presentation, we talked about the 4 main fields of the Modbus message, or the Modbus frame. Notice how here it's indicating the address field, the function code field, the data field, and the CRC. The CRC stands for cyclic redundancy code, and this is a very popular error checking that's used in network communications, in all types of network communications, for protocols that run at all the different layers on the OSI model, and for both DMP3 and Modbus. It's CRC, or cyclic redundancy code. And so this is what's used for error check, and again, this is an example of error checking that's going on at the data protocol, that makes things like parity over a physical protocol unnecessary, because each end is detecting errors. So we've got address, function, data, and CRC. Notice it's indicating the size of each: 1 byte for address, 1 byte for function code. And then here, this varies, because when it comes to, say, the data being returned in a response message, the number of bytes required to return, say, 5 analog inputs or 15 digital inputs and so on, it's going to vary from message to message, because it's going to be dependent on how many points were requested. So notice how there's not a fixed number of bytes here. One thing to note, however, is that this whole frame in total cannot be more than 255 bytes. So you might even want to write that on your Modbus handout if you've printed it. Is you could indicate that this whole combined message, including CRC, data, function, and address, cannot be more than 255 bytes. Now over here we've just given you a table to help in any of your hex
or decimal conversions from binary or to binary. So when we think of a 1 byte value, we don't generally express that 1 byte value or communicate that 1 byte value as all the ones and zeros that make up the message. And you know, not only does that take a lot more to communicate, it's also much more prone to error. So let's say that our address field was indicating a slave address 10. A slave address 10 would be 0A as a hex value. So we could say 0A is our address field. You can easily communicate 0A. But if we were actually to communicate that as binary, that would be 00001010. You can see how communicating that isn't as efficient, and it's a lot more prone to error. So we simply, and there's an example of an error, we simply shorten that or shorthand it, make it easier to communicate as a hex value of 0A. So yeah, so that's why we have the hex conversion table here, because as an example, in our communications analyzers like ASE 2000 that we'll be using in the lab, we're going to see all the Modbus messages represented as hex values. And then if we want to determine binary values or decimal values, we just have to do a conversion. That's where you're going to want to use your calculator to do number systems conversions. So I'll go over that in our next class, how to use your calculator to do these conversions. But that's really one of the only times you'd be using your calculator in this course, is for number system conversions. Okay, so now that we've looked at that, then we look down here. These are the operations codes. These are the function codes that are either going to be read or write for a specific data type. Now notice how here it's listing the function codes as decimal values. Okay, so this would be called function code 1, 2, 3, 4, 5, 6, 15, and 16. But of course it's represented as a hex value in the function code field. So for the hex value for function code 1 in the hex field, it would be 0, 1. By the way, guys, this 0x that you see here is a way of indicating when you're communicating a hex number that this number is hex. So if you see 0x, you know the number that follows is in hex. How would you know the difference between, say, 06 hex and 06 decimal unless you actually have this 0x here? It allows you to identify. So obviously down here as 0f, that's corresponding to 15, and 10 is corresponding to 16. So let's look at these functions. Notice how these functions are either a read or a write. In the command official documentation for Modbus, it calls these writes forces and presets, but we can see their actual functionality is a write. So let's take for example a digital input. A digital input is an input register, and so we know it's going to be a read-only register. And let's find the function code that is corresponding to a digital input. Read input status reads the state of a digital input, which is function code 02. So what's the function code to read a DI? 02. What's it called? Read input status. As far as Modbus goes, what is the function to read the state of an input register for a single point, or a 0 or a 1, or a digital input? Analog then, how do we do that? Reading only of an analog input or a counter or accumulator can be done with a 04 or a read input register. Okay, what about our write values? How about if we're going to write a digital output? It's called for single coil, it's 05, and it's to write the value of a DO. Notice how, because it's an output register, we know it's a read-write register. So where are we going to find the reading or confirmation of a DO that's been written? We'll find it in 01. It's called a read coil status, and it's read state of a DO. So we can write a DO, we can read it. We can write an analog output with a 06 preset single register. We can read it with a read holding register of a 03. You get it? So we've got our reads, we've got our writes, we've got reads and writes for output data types, we have read only for input data types. Okay, so that's as far as I want to go with that for now.
Okay, so we looked at the Modbus handout and saw the function codes and operation codes that were used to either read or write a specific data type being sent out as a request. So now if we look at the response then, we're talking about the response for the function field. And if we're talking about a normal response, that's one we would see in the usual case. It's where the server echoes back. It's the same function code that was sent in the request. And that's your indication that it's a normal response and that you can trust the rest of the message in terms of the data being retrieved, and that it's indicating the true real-time values for the points. But there is times where the server takes exception to that response, and it means that it didn't like the what was being asked. Maybe it was the wrong address for a certain data type. Maybe it was the wrong data type for the address that was being sent. Or maybe it was requesting a data type that wasn't even available, or trying to write a counter that was a read-only counter, things of that nature. So that means we're going to have something called an exception response. And what it means is the function code will be echoed back again, but there will be a 1 in the most significant bit, and that will be the way that the server essentially sends a flag to the master to say, I didn't like your request, and I will tell you specifically what I didn't like about the request in the data field. So this is where you're going to find specifically what the server didn't like. But the function code being echoed back as what was sent, but with a 1 in the most significant bit, is essentially a flag. So this 1 in the most significant bit is the exception flag. And it's simply saying, okay, I'm flagging you with a 1 here to say I didn't like that. And then what specifically didn't I like? I'll tell you by a specific code, and I'll put that in this field, in the data field. So this is called an exception response. So in this example, we see where the function code was actually a 0-1 function code. And if you were to look at your Modbus handout, you would see a 0-1 function code is a request to read a digital output, read coil status it's called. And if it was a normal response giving you coil statuses, it would simply echo back this value. 0x01 would come back as the function field. But because in this case, when we see the example below, we were flagging an exception to that read coil status, the server put a 1 in this most significant bit location and echoed back the function code to make it 0x, remember that's a hex number, 0x81. And if you look at converting this binary string into hex, you would have 1000 equaling 8 in hex, and 0001 equaling 1 in hex. It would be the function code exception would be 81. A flag indicating an exception, and then the same function code echoed back as a function code 01. So we'll talk about exception codes specifically in later on in the presentation, and we'll look at codes and what they mean. But for now, it's good enough to understand that the exception code itself will be found here in the data field, and those exception codes can be found on your Modbus handout as well. So when it comes to the request in the data field is where we essentially see the number of points and the start address for the specific data type that's being requested. So remember, in the function field, you'll find either a read or a write. then you're reading or writing a specific data type. So that will also indicate a data type. But here in the data field is where for the request we're going to say start at address whatever. Then we need to know how many addresses we want to read, so we're going to indicate that by number of points, points or addresses. And that'll be, of course, a number. Okay, how many addresses do you want to read or write? The maximum size is 251 bytes for the data field. And if you think about it, that makes sense, guys, because remember I said that the maximum this whole message could be is 255 bytes. So if we know this one is 1 byte, we know this one is 1 byte, and we know the CRC or error check is always 2 bytes. That means that leaves 251 bytes for a maximum value. Okay, so for the request, it's very standard just to have start address and number of points. This is where I want you to start in the data map, either reading or writing, and this is how many points I want you to read or write. Maximum size then, 251. Then when it comes to the response, this is where the server is returning the data that was requested. It's returning the data starting at a certain address, and it's returning the number of points that were requested. Now, due to the 251 byte limitation, it could mean that for a response, there's not enough room in that frame to return as much data as was requested, and that's where there's a part of the protocol is to sort out how to do that. And really it comes down to there would be an exception saying you asked for too much data, and the master would essentially have to return with multiple requests to get that amount of data. So that's what it says here. You may need to send multiple requests to get all of the data. That's not usual at all in Modbus. Remember I said that in industrial networks there's actually not a lot of data being moved back and forth during a session or during the time that a client's talking to a server or a master to a slave. So rarely is there a situation where multiple requests have to be sent to get the data from a single data type, if that makes any sense. So then lastly we have our CRC. It's always a 2-byte value. It's called cyclic redundancy code. It ends every message. It doesn't matter what the size of the message is. At the end of every message is a 2-byte CRC, whether it be a request or a response. And it's checked upon receipt. Essentially what happens is there's what's called a CRC algorithm calculated for all of the ones and zeros that make up this part of the message, and that calculation is sent along with the message, and at the receiving end the receiver does the same. It calculates using that same CRC algorithm, and it compares its own calculation to the one that it received, and if it's the same, then it concludes that there's no errors. That's called CRC, or cyclic redundancy code. You could even go on the internet and look up cyclic redundancy code for Modbus, and you could enter all of the hexadecimal values in a message and hit equals, and sure enough you'd be able to confirm some of the CRCs we're going to see communicated in the lab. When we look at a raw message between two devices, we'll be able to look at that CRC, and if we wanted to, we could go on the internet and bring up a CRC calculator and confirm those values. So that's called the error check, or the CRC. When we look at these function codes, these are the ones you're going to find on your Modbus handout. They're the most used and popular of the function codes, but it's good to know there is other function codes available, and there's also user-defined function codes where, because it's open source, you can make up your own function code and have it, say, read a video file or a sound bite or some other data type that doesn't fall within these categories here, or these categories. Okay, but for the purposes for this course, we'll just understand there is more function codes, but we are going to concentrate on the ones that we see here, bolded in red. These are called the public function codes, and then you can have the other ones, like all of these are public function codes. You can have user-defined function codes after that. So notice how it says user-defined function codes are 65 through 72 and 100 through 110, implemented by the user. Okay, so this is where we'll take a look at our first function code and how it's formatted for both a request and a response, and we'll find that on our Modbus handout.
Okay, just back to the Modbus handout here. We did mention exception codes and how an exception code would be flagged by having a 1 in the function code field placed in the most significant bit. But that was just a flag to tell the client or the master that the server wasn't happy or had an exception to what was being requested, whether it be a read or a write function code. It's echoing back the same function code, but with a 1 in the most significant bit. The exception code itself, which you'll find here as a 1 byte value, these are all 1 byte values. These will be placed in the data field right up here when the response comes back. So there'll be a flag here, and then the actual exception code saying what the server didn't like, or what the remote or the slave didn't like, will be found in the data field. So that's going to be a 1 byte data field where it contains the exception code. So I just wanted to look at that a little bit. We'll look at specific messages that include these and how it's flagged in the function field and indicated in the data field when we look at specific Modbus messages. But for now, I just kind of wanted to let you know that's where these exception codes come in. They'll be found in the data field for a response where it was already flagged in the function field as having an exception to what was requested. All right.